Hi, this is Barrett Givens from Cal Poly Pomona, and in this video, I'm going to talk about how to find one pair of integer solutions, x and y, to an equation of the form ax plus by equals c. And I'm going to do that in this case by working through these three examples and then just sort of talking about what the general case would look like. So all three of these examples, I'm solving an equation of the form 15x plus 9y equals a constant. So let's do the first one first. Number one, 15x plus 9y equals 3. 15x plus 9y equals 3. Well, we can see that that actually has the form 15x plus 9y is equal to the GCD of 15 and 9, because the GCD of 15 and 9 is 3. And we know that the extended Euclidean algorithm allows us to solve that. So let's go ahead and use the extended Euclidean algorithm to solve that. All right. So the extended Euclidean algorithm, you start by doing the standard Euclidean algorithm to find the GCD of 15 and 9. So 15 is 9 times 1 plus 6. 9 is 6 times 1 plus 3. And 6 is 3 times 2 plus 0. And so we see from that, as I said, the GCD of 15 and 9 is 3. Now I'm going to make a little table that allows me to find the solutions or a solution to the equation 15x plus 9y equals 3. So this is the extended Euclidean algorithm, one form of it anyway. Up here, I'll make this table. Up here in the two columns on the right, I'll put 1, 0, 0, 1, which I can remember because it looks like the identity matrix. Over here on the left, I'll put 1, 1, 2. That comes from the quotients in my Euclidean algorithm. And then I'll do this recursive property where down each column, I'll take the quotient times the previous value of x times the one up above it. So I will do 1 times 0 plus 1. That's 1. Then I'll do 1 times 1 plus 0. That's also 1. And then I'll do 2 times 1 plus 1, and that is 3. Then I'll do the same thing with the second column. 1 times 1 plus 0 is 1. 1 times 1 plus 1 is 2. And 2 times 2 plus 1 is 5. Okay, just as a check, down here at the bottom, this number 3, this is 9 divided by 3. And that number 5, that's 15 divided by 3. Those are the values of A and B divided by the GCD. And so that means I've done this correctly, okay? Then my answer will be these values 1 and 2 right here. Okay, so I will have x equals and y equals. I also need to think about one of them will be negative, and I need to go ahead and annotate these with negative signs. So on the first row, it's the second column that's negative, and then it alternates from there. And so I'm getting the first column goes with the bigger number. The bigger number is 15, so that's x. So x is -1, and y is 2. All right, so I found one solution to 15x plus 9y equals 3 using the extended Euclidean algorithm. X is -1 and y is 2. Let me just move this up a little bit. And, I can double check by just plugging in those values for x and y into the equation 15x plus 9y equals 3, and I get that it's true. Okay, so I did it correctly, so that's good. All right, so that's the first kind of example. That is the situation where you're looking at ax plus by equals, and you have the GCD. Okay, 3 is the GCD of 15 and 9, and so that's how that worked. All right, now for the second one, 15x plus 9y equals 11. Well, let's think about that one for a little bit. I think about the GCD of 15 and 9 is 3, so I can factor a 3 out of the left-hand side. So I get 3 times 5x plus 3y equals 11. Now, if I had integer values of x and y, then this would look like 3 times an integer equals 11. If x and y are integers, if there exist integer values for x and y, then 3 divides 11. But we know that 3 doesn't divide 11. 3 doesn't go into 11 evenly, so that's a contradiction. So that tells me that there do not exist integer values of x and y. And so we can say this one has no integer solutions. No integer solutions. So that's another thing that can happen in these problems. When you have ax plus by equals c, but the GCD of a and b does not divide c, then there will be no integer solutions. Okay, so that's the second kind that could happen, is where you have ax plus by equals c, but the greatest common divisor of a and b is not a factor of c. Then there are no solutions. All right, and then the third case, 15x plus 9y equals 24. Okay, so what I'm going to do is I'm going to say, well, I already have kind of a related solution. I have 15x plus 9y equals 3, and this is close. So what I'll do is I'll make a note that I just found that if I let x naught equal -1, or let me call it actually x prime. If I let x prime be -1 and y prime be 2, then I get 15x prime plus 9y prime equals 3. Okay? If I let x prime be -1 and y prime be 2, from the first question, I know that that's a solution to 15x prime plus 9y prime equals 3. Now, 3 does divide 24, the constant on the right-hand side. So what I'm going to do is I'm going to say, well, 3 goes into 24 8 times, so let me multiply both sides of this equation by 8. So I multiply both sides by 8. I'll distribute that 8, and I get 15 times parentheses 8x prime plus 9 parentheses 8y prime. So I'm using the commutative and associative properties for integers equals 24. So that tells me if I'm looking for something of the form 15x plus 9y equals 24, I should have x be 8 times x prime and y be 8 times y prime. And that gives me that x is -8 and y is 16. Okay, so these are these 3 examples that I've worked out now. And these are really representative of the 3 types of problems that you could get in these of these types. So whenever you're trying to solve ax plus by equals c, there will be 3 possibilities. We'll have 3 possibilities. We'll either have that c is equal to the GCD of a and b, or we'll have that the GCD of a and b does not divide c, or we'll have that the GCD of a and b does divide c. Okay? When c equals the GCD of a and b, then we can use the extended Euclidean algorithm, as we've learned in an earlier video. When the GCD of a and b does not divide c, then you can simply just say there's no integer solutions. And when the GCD of a and b does divide c, then you can take the answer that you found for when c equaled the GCD of a and b and just multiply that answer by an appropriate amount to get the answer to this new equation. Okay, so for example, in number 3 here, we had to multiply by 8 because 3 goes into 24 8 times. All right, let's just summarize then these 3 concepts. So when we're trying to solve ax plus by equals c, and we're trying to just find one solution, let's assume that a and b are greater than 0 for this chart, and we'll let d be the GCD of a and b. So the first case is that d does not divide c, and in that case, we can say that there are no solutions, no integer solutions anyway. The second case is when c is equal to the GCD. Then we find one solution, x naught, y naught, using the extended Euclidean algorithm. The third case is when the GCD, d, divides c, but c is strictly bigger than the GCD. So then first you solve ax plus by equals d using the extended Euclidean algorithm. That gives you some solution x prime y prime. And then you multiply by the number n, which is how many times the GCD goes into your number c. Okay, n is equal to c over d, and your x naught will be n x prime, and your y naught will be n y prime. All right, and so that means that we can sort of completely understand an equation of the form ax plus by equals c. We can always know if it has solutions or doesn't have solutions because these three cases give us all three possibilities. We know that it doesn't have solutions if c is not divisible by the GCD. And if c is divisible by the GCD, then we know how to find a solution using either the extended Euclidean algorithm or the extended Euclidean algorithm and then multiplying by some constant. All right, and that will always give us one possible solution, just one solution that we can find using these methods. So just to go one step further, there's a few consequences we can figure out from this. So first of all, we can say that the equation ax plus by equals c, that has integer solutions for x and y, if and only if the GCD of a and b divides c. Okay, and we know this theorem is true because on the previous screen, I just told you how to find the solutions, okay? If it has integer solutions, then that means the GCD has to divide C, because if the GCD does not divide C, we have no solutions. And if the GCD does divide C, then we have algorithms, we have methods where those will always work and give us solutions. Now, a nice corollary to that is if you look at an equation that looks like ax plus by equals 1, well, that will have solutions if and only if the GCD of a and b divides 1. But the only positive number that divides 1 is 1 itself. And so we can say that ax plus by equals 1 has integer solutions if and only if the GCD of a and b is 1. The equation ax plus by equals 1 has integer solutions if and only if the GCD of a and b is 1. This is an extremely important corollary, an extremely important corollary, deceptively important, okay? It might not feel that earth-shattering, but it's extremely important and will be used a lot in proofs in number theory. As one example, here's a lemma that we can prove using that corollary. Suppose the GCD of a and b is 1. If a divides bc, then a divides c. All right, so let's go ahead and prove this. Let's prove this. Proof. Suppose the GCD of a and b is 1. And let's also suppose the hypothesis a divides bc. Okay, so now if we assume that a divides bc, we can use the definition of divides. So we can say then bc is equal to ak for some k in the integers. And then the fact that the GCD of a and b is 1, oftentimes in a proof, if you're given that the GCD of a and b is 1, then what you want to do is you want to use this corollary. This corollary says that the GCD of a and b equals 1 is equivalent to saying that ax plus by equals 1 for some integers x and y. So I'll put comma, and ax plus by equals 1 for some x and y in the integers. So the power of this corollary is it lets you take a statement that looks like GCD of a and b is 1 and convert that to an equation, ax plus by equals 1. And in a proof, having an equation, it's like then it's something that you can manipulate and, substitute and do things. Now, what are we trying to get to? Our goal, let's make a little piece of scratch paper over here on the side. Scratch paper. Our goal is to get to C, A divides C. So that means we want to have A times something equals C. We want to have A times something equals C. And the something has to be an integer, right? I'll put a little arrow there and say integer. We need A times an integer to equal C. Now, you might sort of think, oh, well, why can't I just take this equation right here and then divide by b, right? Then I would have c is equal to a times k divided by b. But I don't know if k divided by b is an integer. In general, we want to avoid division because when you divide, you don't know if you still have an integer. So I can't just divide. We want to avoid dividing because then we won't know if what we have is an integer. What I can do instead is I can look at this last equation, ax plus by equals 1. Well, my goal is to end up with something equals c. And so that's going to motivate me to multiply this equation, ax plus by equals 1. I'm going to multiply both sides of that equation by c. Multiplying by c yields acx plus bcy equals c. Okay, so I'm getting closer to my goal because my goal was to have a times an integer equals c. Well, I have something equals c, okay? Can I factor an a out of the left-hand side? No, I don't think I can. I can factor an a out of the first term, but not out of the second term. What else could I do? Well, I see that BC right here, this BC right here, BC, but I know that BC is equal to AK. And so I will substitute AK for BC. So I get ACX plus AKY equals C. So I'm getting closer to my goal because my goal is to have A times an integer equals C. Well, I have something equals C. Can I factor an A out of the left-hand side? Yes. A times CX plus KY equals C. Now, is this A times an integer equals C? C, X, K, and Y are all integers, and I'm not doing any dividing, I'm just multiplying and adding. And so, yes, that's an integer. So I can say since Cx plus Ky is an integer, then A divides C, which is what we wanted to show. Okay, so the point of this video, there's sort of two main parts of this video. The first part is that we can completely solve equations of the form ax plus by equals c, depending on how c is related to the GCD of a and b. And we use a combination of either sometimes there's no solutions, or we have to use the extended Euclidean algorithm, and then sometimes we have to use the extended Euclidean algorithm, but then multiply by a constant. And then the second part is that algorithm, that process tells you that we know exactly when ax plus by equals c. And in particular, we know when ax plus by equals 1, which ends up giving us this extremely important theorem or corollary that is used in many proofs. Whenever you're given that the GCD of a and b equals 1, then in a proof, you can say, well, that means that I have ax plus by equals 1 for some integers x and y. And we did an example problem proof using that corollary. All right, thank you for listening.